record this lesson. I'm going to record it just in case. I already recorded the morning, so you have that. But just in case this one's better. I think the mornings was quite good, but. Sure. Okay, so I'll go over some, this is in preparation for the exam, but just to zero in on the electrostatics again to prepare you as well for the upcoming test. I'll focus on electrostatic questions. Make sense? These are word problems. You're not going to get word problems on the test, but this is primarily to help you with the exam, but this is an overlap for the test as well. So here. I just, oh, I don't like that. Glimmer. Okay, so you've got a positive plate here. Negative plate here. Okay. Okay, draw, don't tell me, but draw it in the direction of the field lines. Come up with an equation that relates. The distance between the plates and the electric potentials to the electric field. So number one, direction of field. Number two, what is the equation for electric field? I mean, we'll add a lot more to this, but let's start with that. See if you can get it. Okay, so first one, direction of the electric field. It's a definition, you just have to know it. The direction of the electric field is defined as the direction that a small positive test charge when moved, if placed in the field, which way would it move? Yeah, down. That's the direction of the field. Field is down. Always away from the positive towards the negative. It's just defined in terms of the positive test charge. Call it small q. What is the equation for the electric field in terms of the electric potentials and the distance d? Yeah. So it's VB minus, whoa. VB minus VA over D. The short way is just VBA. That stands for VB minus VA. Okay, what about this? Does this apply as well? Yes or no, you write it down. Because that's a real equation. Okay, this, keep in mind that this is parallel plates, right, that we just were looking at. This equation is used for what's called a point charge. That's a point charge. Draw the field lines around that point charge. Draw them out, see how they're different than the plates. Field lines are like rays of the sun. They diverge. I drew it at an angle, but whatever. Still. I love the fact that I practiced straight line drawing so long. It's perfect now. It's outward, right? From a positive charge, field lines out. Notice the difference between these field lines and the ones above. These spread out like rays of the sun. These are all parallel. You can only apply this equation here. This equation here, you can, this equation here, you can only apply in the case of a point charge. That's your big Q. Right? You cannot apply this equation to the parallel field lines, to the plates. For that, you need what we just wrote down, this equation here. Mm-hmm.
I have an equation that says E is equal to change in V over change in R. Is that the same thing?
Yeah, I don't know why they wrote it that way.
Okay.
I didn't write that. That's, I think, from the workbook. So it's this one here. Rewrite it. You can rewrite it. I don't mind if you rewrite it on your formula sheet. You can do that. Okay. So it's important. I kept saying these are like rays of the sun and these are parallel. This set of field lines is what it tells us, that the field is uniform. It's a uniform field What does that mean? So that's your next question. What does uniform mean? What does it imply? Once you write down everything you know, once I tell you it's a uniform field, and you can see that from the parallel field lines, what does that imply about the electric field, the force, the acceleration? Okay. So uniform means constant. It's a constant electric field. What does that mean? Well, I didn't write that properly. Constant electric field. What does it mean? If you go back here, that means it's the same value here as it is here, as it is here, as it is here. It's the same anywhere within this sandwich of parallel plates. That is not true here. The field is higher here than it is here. It decreases the farther out you get. So it's not constant here for this case. So what's the big deal? If the field is constant, that's important because that means the force is constant. I'll write it here. The force is, because force is constant. Why? Because E is, write another equation in terms of F for E. Complete that. This is the general equation. This is applicable in any case, whether it's parallel plates or a point charge. Complete that equation. It's a definition. I mean, electric field is just force divided by that small charge. See that small charge there? You could find the force divided by that small charge. That would be equal to your electric field. And the point is this: if this is constant, it's because that's constant. Well, that's messy pretty, but you understand what I mean. It's constant. It's the same everywhere. So all you have to know in order to calculate the force, all you need to know is the electric field. You know what the force is anywhere in the plates, no matter what the question, you know what the force is. It's the same at each point. And what is this equal to? If you knew the electric potential and the distance. Equal to VBA over D. So you could find the force if you knew what the voltage was of the plates and the distance between the plates. And with this charge here, let's say this was on the ground, a real, like, this is on the floor, let's say. What other force would be acting on that charge? First of all, what direction is the electric force acting on that charge? You already mentioned it. Which way is it again? Yeah, it's down. That's down, eh? Okay, that's not gonna work. Sorry. Replace this. This will work. Replace this with a negative. Which way is the force acting on, do the electric field, which way is the force acting? Down or up? Yeah, up. It's attracted, it's a negative charge. It's attracted to the positive. In the opposite way to the field because it's a negative charge. That's Fe. Okay, now we're on the floor. This sandwich parallel plates is on the floor. Is there any other force that's acting on this charge? Any other force acting on that particle? Yeah, gravity. Which is acting down. Okay, yellow doesn't work. Whatever. Or greenish, whatever. Okay, if it's sitting there, what can you say about these two forces if it's stationary, if it's not moving? Pardon me? What's equal? Yeah, good. If it's stationary, and what's the equation for Fe in terms of the electric field? This is a charge Q. In terms of Q in the electric field, what's Fe? Q times, yeah. And what's Fg in terms of the mass? Yeah, M times G. Okay, I'm not going over obviously specifics. I'm just going over general concepts you need to know. Gosh, my drawings are getting better. Praise the Lord. Okay, let's go on. Second major question. Concepts behind you need to know. That's a charge, big Q. And you have, let's call this position A, position B, and they're just final. Do I want to do that? I'm going to change it slightly. Sorry. Put a negative. Let's say this is an electron. First of all, what's the charge on the electron? Look it up. Where are you going to find it? Could be a proton as well. They're the same charge except opposite. Tell me where that is.
Negative 1.6 and 10 to the negative 19.
Yeah. That's your what's called elementary charge. So what's this charge going to do? I placed the charge, this electron at point A. What's it going to do? Be repelled. Which way is it going to move? Yeah, it's going to move towards B. Starts at rest. So let's say it's going to reach some final speed here at B. It's moving in what? What would you say this electron is moving in? Not moving in a, it may be a vacuum, but there's something in the background. What is it? It's not sitting in space. If I let it go, you just said it would be repelled by big Q on the left. So it's sitting in something. It's moving through something. Good. It's moving in the field. What's this moving in when I let it go? I mean, if I let it go in the middle of space, somewhere away from the Earth, it would just sit there. But it's not sitting there; it's moving. So before I let it go, it's sitting there, but it's sitting again within some background. What is that background? Gravity. It's a field. Okay, let's call it conservative field. So, anyways, my point is that both fields act in a similar way in that the energy that this pen has up here is conserved. Doesn't disappear. It's transformed into kinetic. Same thing with this case here. The electron's potential energy doesn't disappear. It's transformed into kinetic. What's the law that we use to express what I just said? No, it's even more fundamental. Yeah. Say it. Yeah. Yeah, you can say it in different ways, but yeah. Delta KE is? Yeah, what's this law called? Conservation. Stays the same. Something's equal to something else, it stays the same. It just changes form. The left side's, it doesn't matter what type of field it is. The left side's always 1/2 mvb squared, in this case, minus 1/2 mva squared. What is 1/2 mva squared? What's that? What's it equal to? What's VA equal to? I let the electron go, let it do its thing at point A. You just said it would be repelled by big Q. So what speed did it start at?
0.
Yeah, so this is 0. What is the potential or change of potential energy, not in a gravitational field, but an electric field? What's it equal to? Doesn't matter whether it's parallel, whether it's a point charge or it's parallel plates. It's the same equation. What's the change in potential?
Like U bracket something.
Q times.
Can't really.
See how memory helps? See how much time you waste because you don't remember? If anyone says don't memorize, that's not true.
You changing.
Yeah, that's good. VBA is changed. Yeah, that's what VBA is. Good. VB minus VA. Which means, go back to the diagram. This has got a VA. It's got an electrical potential, and so does B. What's the equation for the electric potential of a point charge? Very similar looking to the electric field equation. What is it for a point charge? K is in front. Big Q is what causes it. It's what causes the field, so it's what causes the potential. Divided by, is that right? That's electric field, though. Can't be both. There's no squared, it's just R. And this is a scalar. You can't represent this with vectors. It's much easier to deal with an electric field because of that. But there's less information that contains. So VA is just that, where RA is, that's RA. Okay, what about VB? KQ, same source, except over R, B. Draw in RB. Where's RB? From what to what? Draw it in. from the charge, the source charge Q to, yeah. Let me just finish drawing my spectacular straight line. And don't get jealous. It took me a while to actually be able to draw all these circles and straight lines. I know some of you are thinking, why? Why does he get all those skills and I draw lines like that? It's just the way it is. Don't be jealous. If you practice enough, you too can be master of the straight lines. Circles. I wonder if I can draw ellipses. How the heck did that happen, man? What the heck? I don't understand.
Oh.
Yeah, okay, again, don't be jealous. It's just something that I'm a natural at. Back to this. Look, guys, you can calculate VBVA if you know what this charge is, what the distance from that charge to each of the points is. Right? What do you need here? What mass? The mass of what particle? Yeah. Which you can look up. I mean, look it up for me, see if you can find it. Yeah, so it's in your formula sheet. Yeah, it's in that too. Did I complain about my ringing to you guys, or was that yesterday's class? Oh, you guys have to pray for me too. I have ringing in my ear. Yeah, it went away for a while, but it's back. You what? Yeah, but you're young. It's not what I think mine. I don't know if it's hearing loss. I put on. Why am I telling you this? I put on a headband. I was listening to music at night to fall asleep, and I think what happened is I left it on to, like put the maximum value or volume on, and I didn't notice it because it was slipped out of place, and maybe it slipped over the ear, so it was like maximum volume. I think that's what happened because I've never had problems before. My doctor I talked to, and I talked to him about it, and he says it's probably hearing loss. I didn't believe him at first, but he might be right. And he said he'd set me up with a specialist in July. Tinnitus, yeah. I think I'm onto something. I think I may have discovered something. So pray for me. I appreciate it. I'm trying some of these special eardrops. I'll let you know if it works. Anyone in your families have it? I might be onto something. I'll let you know. Anyway, but pray for me. I appreciate it. Okay, back to this. So you know everything you need in order to solve for this. What you're trying to solve for is the speed. This is a little confusing, but notice I put these in different colors. That's the speed. Sorry if it's confusing. That is the electric potential. It's a bigger V. You're trying to solve for the speed. Trying to solve for this. That's what you're trying to solve for. Okay. I'm going to go over some more problems. What time is it? 12. Yeah, we got lots of time. Is there anything else I wanted to ask you about this problem? What is this similar to, this problem that we just went over? You're moving from what would you characterize this point A as? High or low potential? Pardon me? Is this high or is this low potential?
Pretty high.
What happens when you let it go to that potential? What happens to this potential here when you let the electron go from A? What increase? What changes? Kinetic increase is the same as this when you let it go. So again, the question is, what is point A? Is it a position of high or low potential? High, because when you let it go, after it's let go, it increases its kinetic. It loses its potential. So if you're losing your potential, it's similar to losing potential here. You're losing potential. You started from a high, you're going to a lower potential. This is high. This is low. Position B is low. Similar to falling, it's sideways, but it's similar to falling towards the ground for the pen. Going from high to low potential and speeding up as a result. Okay. What would this be similar to? I don't like that. You're going from A to B. And this is you're going from A to B. What would be happening to your potential? What happens to potential? Describe it. And then 2, how would you calculate the difference? Calculate that. Add it in whatever you need in the diagram. Okay, so what happens to potential energy? How would you describe it? Oh, wow. Yeah, it increases. You're raising your hand. It's good. It increases. Yeah. What's that? Potential entity B is greater. What's that analogous to, similar to, in the gravitational case? You're increasing your potential. What's that similar to? What are you doing? You're raising your bloody hands. Okay, screw you. I'm gonna raise my hand. Can I turn it off? Enough. Getting bored with my, okay. So it's similar to lifting this pen up to a higher potential. Okay, how do you calculate the electric or the change in potential? You need the VA and the VB, which means you're going to need RB, and you're going to need RA. Okay, you'll also need small charge that's moving, and you need big charge, which is the source. So in other words, change in potential is equal to QVBA. That's a short way of writing it. This is the longer. Whoa. Where VA or VB, well, I'll write both. KQ over RA. VB is KQ over RB. That's what you need. Okay. Okay, let's look at it. Are these applicable to parallel plates? Can you use that for parallel plates? What do you think? No. Because, yeah, they're for point charges. And let's look at this situation. I don't know, which question is this? I'm losing track. Oh, what happened? Crap. Whatever question is, let's do another one. Yep. These are plates. Oops. And you shoot, I don't know, say a negative. I like my electrons. You notice that? I couldn't. Electrons going through these plates towards a negative plate. So it's already moving, but it's going to slow down. It's going to slow down. It's going to slower, slower, and slower, slower, till it reaches VF is 0 at this point. You call it VB, I guess, if you want. Okay. You're given this speed. Let's say, I don't know, I'll make it up. 1.5 times 10 to the 6. And that's an electron. It's a small little electron. So the charge is negative 1.6 times 10 to the negative 19 coulombs. And what else? I don't know. Let's say I know this chart. Let's say this is 600 volts. This is my VA. And my VB, I don't know, is negative 100. Can you figure out? Well, I gave you too much information. Erase that. Can you figure out the potential difference? Can you do that? Set it up. You don't have to calculate it. See if you stop raising your hands. I have to turn that off. Oh, you do have a question.
On the test, will it like, do you have to assume it's an elementary charge or like will the question say if it's an elementary charge? So
I can't see you because I'm getting flushed out by all these hand raises. It'll say what charge it is. Yeah.
okay.
Yeah.
Why is the negative charge going towards the negative?
You're shooting it towards it and it's slowing down as a result. It's akin to or it's similar to shooting a bullet up. Eventually it's being pulled on. In this case, it's being pulled on by the positive and repelled by the negative. It's going against the field. Or the direction, yeah.
Would it just stop before the field or would it start going backwards?
It would what would the bullet eventually do? Yeah, same thing. Okay, set it up. Calculate that potential difference. See if you can do that. What do you think, guys? So if it's similar to me firing a bullet up or throwing a ball up, what law comes to mind? Similar to the gravitational case. What would you apply in the gravitational case if you were trying to, let's say, solve for the speed, the initial speed, let's say, of the ball, throwing it up in the gravitational field? You say it louder?
Final minus initial.
Yeah, it does involve final minus initial. What's the law? Does involve, it involves a gravitational field in that case. You start off with, I'll give you a hint, you start off with using the potential energy. Yeah, same law as before. But instead of speeding up, you're slowing down. So this, just reverse it. Put the potential first. Put the kinetic last. Potential is Q VBA. That's what you want to solve for, your VBA. What Q is this? Which Q? What's moving? Yeah, the electron. So you know what that value is. And on the right side, you've got in brackets. What's that term equal to? I should put B, not F. Doesn't. Yeah. Do you have this? Can you figure out what that kinetic energy is? It's an electron. Do you have everything you need? You have the mass of an electron? Yeah, you can look it up. You have the initial speed at point A. That's your VA, by the way. Yes, you do. Not zero. It's 1.5 times 10 to the 6. It's 15, what? 1.5 million meters per second. So you can solve for your potential difference. Interesting. Okay, if you knew this voltage here, let's say you figured out VBA was, I'm making this up, but let's say it's 900 volts. You figured it out. It's 900 volts. That's your VA. How do you calculate VB? Okay, so what's VBA equal to? I think this is what you meant. What's VBA equal to? Yeah, good. So you'd have 900, because you would have figured that out, is equal to VB, which you don't know, minus 700. So what's VB? 900 plus? Yeah. Yeah. Volts, obviously. What time is it? Yeah. I think that was kind of a tie. This morning's lesson was pretty good too. Not bad. Not bad. I'm just going over whatever else you can help. Get help, please. Yeah, study for your test. You got 15 minutes. Study for the test or catch up on the notes, the assignment that's due tomorrow. It's a lot of pages to do for the assignment, right?
Do you want us to do the questions too, or is it just a note?
Just the notes. Yeah, I do the examples as well. You don't have to draw pictures, but you can if you want. You have up to the end of tomorrow night to get it in. I usually check on it Saturday morning, so even then it's fine. You like raising hands a lot?
That's good.
Yeah.
Probably good.
We got more time for fog, right? We got a lot of time. We'll go over a lot more questions. I can even double up on this if you want. But I don't know if I want to do that. I might do that during the end. In other words, I can do one lesson in the morning and a different lesson in the afternoon. So you have 2 recordings.
What would that be covering?
That would cover the whole. We're going to probably get through everything that's needed for the exam, anyways. So we got a whole. How many more days do we have?
2 in person for us.
So 5 total.
What days do you have?
The 14th.
14. Yeah.
Not this week, not this.
Is there a person there?
I think what. Oh, that's the problem.
So lucky.
We should just write on Wednesday.
I'm not in control of that.
It's not.
So I mean, it's up to you. I could double up on the lessons, but I think we got more than enough time to go over all of it. So
Wait, is the exam like, is like, there are a lot of like multiple choice?
there's,
25 and 5.
what did I say? Yeah,
25 and 5. 25 multiple choice.
it's about 25, 27, 28 multiple choice.
The question is evened out like between the units.
That I haven't looked at. Usually it is the way I set it up. And, yeah. To take another look at it. It's at home. The one I'm pulling from is an older one, but whatever. Okay, so that's it. You can, hope that helped.
We have to do our test 2, right, on Monday?
Yeah, you got to do your test. Give me a second here. It's electrostatics quiz.